All right, this is going to be the video for differential equations, section 7.3, day 1. In 7.3, we have a lot of information about properties of the Laplace transform, which turn out to be very, very helpful when we use them to solve differential equations. There's a lot going on here, so we're actually going to split it into 3 separate days. This first day, we're going to talk about what's called shifting on the s-axis. So it's a property of the Laplace transform that makes it much more extensively useful in a much wider variety of situations. All right, so the Laplace transform has a number of properties which are very useful in solving more complicated situations, especially ones in which the driving function on the right-hand side is not smooth and continuous. Right, we've learned techniques earlier where we were able to handle a right-hand side, which was a function like sine of x or e to the 2x or something like that. But what happens if that driving function is something that's modeling, say, an electrical circuit or a mechanical system, and the driving function isn't applicable for all time, maybe the independent variable is time, and we turn on a sine wave driving function, but only at 2 seconds after we start analyzing the system. And up until that, it's 0. Right, so we're going to use properties of Laplace transforms to help us handle situations on the right-hand side like that. First of all, though, we just have to learn how to deal with the properties themselves and how they're applicable. The first property we're going to study today is called shifting in the s-axis, and that's this. If you were to take the Laplace transform of something where it's not just f of s, but all the s's are replaced with f minus a constant, and that could be plus a constant, right? Then the a would be negative. Then it's equivalent to having the same function from the table f of t, except multiplied by e to the at, whatever that a is. It just multiplies by an exponential. And the reverse is true, right? If you take the inverse Laplace of the f shifted in s, you get the f of t, but multiplied by e to the at. All right, so shifting in the s domain is equivalent to multiplying by e to the at in the t domain. All right, and so let's see how we would work with that. Let's say we're given this situation here where we want to take the Laplace transform of e to the negative 2t cosine of 4t, okay? So you would think we would want to somehow take the Laplace transform of the e and the Laplace transform of the cosine and multiply them like a product. But you can't do that, right? The Laplace transform is a linear transform. So you can, if there's a plus sign in here, you could do the Laplace transforms of each of those things separately and add them, right? But multiplication doesn't work that way. And unlike derivatives, there's no product rule for Laplace. Instead, we have to recognize that when you multiply any function by specifically an e to a constant times the t variable, then that has the equivalent of taking this same transformation and shifting it a. So if this a is negative 2, right, then this is equivalent to shifting minus negative 2. So when we're done, we're going to figure out what the Laplace transform of the cosine is, but then we're just going to plug in s plus 2 everywhere instead of s. So that's the way we handle this multiplying by e to the negative t. Identify what a is. A is negative 2, and then write s minus a. And then just figure out what the Laplace transform is of the rest of the function, and then plug in s plus 2 instead of s. So now let's just deal with what's the Laplace transform of cosine 4t. Okay, so we can refer to our table here. And for cosine, it's s over s squared plus k squared. So this is going to be s over s squared plus 4 squared, which is 16, right? But because there's the shifting here, we're going to change, this is going to change these to s plus 2's. So that means that the Laplace transform of e to the negative 2t cosine 4t is s plus 2 over s plus 2 squared plus 16. That's the answer. Okay, so you have to identify what the shift is by looking at what the constant is in the exponential, and then just take the Laplace transform of the regular function and shift it. Okay, let's take a look at other examples of this being used. Let's go the other direction. What if we have inverse Laplace of 2 over s minus 3? Well, this one actually, we don't have to do any shifting here, right? Because in this case, I can just bring the 2 outside. Not sure why we put this one in now that I'm looking at it, because This is just, well, I guess I can see now, because if we look at the table for 1 over s minus a constant, 1 over s minus a constant is e to the at. So this would in fact be 2 times e to the 3t, right? You can also think of that in a way as being 1 over s minus 3, right? Yeah, no, that doesn't really work as well. Yeah, I guess it does, right? Because that's really the same as what's 1 over s? Well, 1 over s is the constant 1, but then you have to multiply by an e to the minus alpha t, right? So we can see from this example where the derivation of this comes from, right? If you thought of this as 1 over s minus 3, which is equivalent to taking the inverse Laplace transform of 1 over s, which is just 1, then that means this would be the constant 2. It would be the Laplace transform 1, but times an extra e to the 3t. And so that's why the Laplace transform of 1s minus a is the exponential, whereas 1 over s is just the 1. Right? So really you can think of this property as kind of a connection of item 1 and item 11 on the table. But that's a very useful property, the shifting property. So let's take another example. Let's say we have this 1 over s minus 6 squared. Okay, well, what we could say is, first of all, what shifting is happening? Pretty clearly, this is s minus negative 6. So my a is negative 6. And that means I'm going to have to plug in s. That's going to be the equivalent of multiplying by e to the negative 6t. So when I'm done, I'm going to take the effect of the shift out and find the Laplace transform, and then multiply the result by e to the negative 6t. I'm sorry, it's just, let me back up for a second there. It's just s minus 6. So the a is in fact positive 6 in this case. And so that's equivalent to multiplying e to the positive 6t. All right, so if you remove the effect of the shift, this is equivalent to taking the inverse Laplace transform of 1 over s cubed, right? And we know that a power is t to the n is n factorial over s to the n plus 1. So if I have a 3 down here, that's equivalent to s2 plus 1, right? Which means I have to have a 2 factorial up here to produce the equivalent for t squared, right? But because I'm missing this 2 right now, I'm gonna multiply the top and the bottom by 2 factorial so that I can write this in the form where it's 1 over 2 factorial t squared, right? And 2 factorial is 2 times 1, so it's 1/2 t squared. Okay, so the last thing is I now, because there was a shift, I'm going to take that and multiply by an extra e to the 6t. So it's 1/2 e to the 6t. T squared. Okay, so that's how the shifting works. You have to identify what the shift is, kind of separate it out, remove it temporarily, and then find the Laplace transform and multiply by an extra e to the at. Okay, now there's some other things that can happen that can make it more difficult to see how to use the property. Let's take a look at those a little bit more complicated cases. Here's one where we were taking the inverse Laplace transform of 2s plus 5 over s minus 3 squared. It's pretty clear that the shift here is s minus 3, where a is 3. So we're going to end up multiplying by an e to the 3t, right? But then that means that the top would also have to have that same thing, right? S plus 3. Let's look at the ones that are something squared. Well, I can do s over, or well, I can do something over s plus 3 squared. Whenever we have a shift here, it's going to turn out to be advantageous to try to get that same shift in the top. So this isn't going to seem intuitive. But let's say, okay, in the numerator, if I've got s minus 3 and the quantity is squared, so I'm going to be treating that as an s squared eventually, I'm going to have to take this s and also try to make it into an s minus 3. You'll see why in a second. So how can I force there to be an s minus 3 up here? Well, what we can do is say this is equivalent to, let me write it over here. We have 2s plus 5 over s minus 3 squared. So what we can do is we can say, well, this is 2 times s plus 5 halves. I can factor out the 2. Okay, and then I can force this s to become an s minus 3 by writing it as, let me do it down here, as s minus 3 plus 3. So I'm going to subtract a 3 and add a 3. So that I can group this one as an s minus 3. Okay, and what that's going to give me is, this is 2 times s minus 3 over s minus 3 squared. Okay, and this one over here is going to be the equivalent of 2 times 3 plus 5 halves, right? So 3 is the same as 6 halves, plus 5 halves is 11 halves, times 2 is 11. So this 2 times this is 11. So this is equivalent to saying we have 11 times 1 over s minus 3 squared, okay? So by forcing this plus 3 minus 3 to occur, minus 3 plus 3, we're able to group this so that this matches this term here. And that means that one of these will cancel, or this will cancel one of these on the bottom, which means now I can write this as 1 over s minus 3 plus 11, 1 over s minus 3 squared. And now when I take the inverse Laplace of each of those, right, I'm going to have, this is just the e to the 3t, and this one is 1 over s squared, whose Laplace transform would be t, right, but shifted 3. So you have the shift, which is e to the 3t, and then times a t. So this is the final result. So by manipulating things at the beginning to separate this, to force there to be an s minus 3 here, even at the expense of making this this constant over here more complicated, we're able to split it into two terms that now are written in terms of s minus 3s. So the way I do that, there's different ways you can go about it, but I just say as soon as I see s minus 3 squared, I try to force that there be an s minus 3 on the top, and I let whatever happens happen over here. That will usually result in some useful cancellation in some way. Okay, so that's one technique. You can force the numerator to have a piece which matches the shifting in the denominator. Another thing that can happen is something like this. Let's say we have this complicated mess here. Okay, so we'll try to factor the bottom, because if I can factor the bottom, then maybe I could try to force the top to look like that. So let's try to factor s squared plus 4s plus 6. That actually doesn't factor, right? If I were to do the quadratic formula, negative b plus or minus the square root of b squared minus 4ac, right? We don't get anything that's factorable because of this. All right, so not factorable. Okay, what do we do if it's not factorable? Well, because we have forms with shifting, if we can still get it in the form of s minus something squared, plus some other stuff, that's going to be useful. So what we're going to do is we're going to complete the square in the denominator. Okay, so you wouldn't necessarily think to try this, but this is useful too. S squared plus 4s plus 6. Is it factorable? If it is, factor it. But if it isn't, then try completing the square. So here's how that works. We could write this as s squared plus 4s. I'll put a little thing here, plus 6, and then minus that same bit. So we're going to add and subtract a certain number here so that we get a perfect square. And the idea being this is s something squared, right? And so what we do is we take this number here, let me just change colors here, this number, and we divide it in 2, so that's plus 2. 2 squared is 4, we write that there, but then we have to subtract the same 4 over here. So we end up getting s plus 2 squared plus 2. So that means we can write this now as 1/2 s plus 5/3 over s plus 2 squared plus 2. So you can complete the square to get this number. And then you can do the thing we did on that other page to try to force there to be an s plus 2 at the top. So this is equivalent to, if I factor a 1/2 out of the whole thing, it's going to be s plus, what happens if you factor a half out of this? That's going to be, let's see, doubling. So it's going to be 10/3, right? S plus 10/3. Okay, over s plus 2 squared plus 2. And then let's do that, subtract 2, or add 2, because I want to make that match. Add 2, and then subtract 2 plus 10/3, so that I can group that. S plus 2 squared plus 2. So then I have 1/2 s plus 2 over s plus 2 squared plus 2. Okay. And then I've got this, which is 1/2 times -2 plus 10/3. So -2 is the same as -6/3. So that's going to be 4/3 times 1/2 is 2/3. So we've got plus 2/3, and then just 1 over s plus 2 squared plus 2. All right. So complicated looking, right? It doesn't look easier here, but if you look at the form of this, this is in the form s over s squared plus 2, whose inverse Laplace transform. Well, what is s over s squared plus a constant? That's a cosine, where this is the k squared. So this is going to be the equivalent of, this is 1/2 cosine of the square root of 2t, but because we shifted s plus 2, remember the shift is s minus, so it's s minus -2, so we have to multiply by an e to the -2t here to handle this shift here, right? Our s has been replaced with s plus 2, which is s minus -2, so this is e to the -2t times that cosine. And this term over here, plus 2/3, is 1 over s squared plus 2, and a constant over s squared plus 2. If we could make that constant the square root of this constant, then it would be a sign. So I'm going to have to do a constant fix up over here. This has to be a square root of 2, so I'm going to have to multiply and divide by a square root of 2, so that this becomes e to the -2t, and then we also have a sine of square root of t, and to get that to match, we also had to have a square root of 2 over here. What's 2 over 3 square root of 2 if you rationalize, although you don't require to do that in this class? You would have, let's see, 2 times 3 is 6, so probably square root of 2 over 3 is the way that would be written. So if you're matching answer in the book, they probably have rationalized it to get this as square root of 2 over 3 e to the -2t sine square root of t, 2t. All right, so this kind of puts all the different complexities together. If you don't already have something that's either factorable, where you might be able to cancel, or then you can try completing the square to get this shifting structure here. Then do the thing we did on the last problem with the plus and minus that number to form this s plus 2. And whatever is left over will form another constant. Very typically, this will be a cosine and a sine pair. Okay, let's do another example like that. All right, we've got inverse Laplace of 2s plus 5 over s squared plus 6. This one's not going to be factorable. Let's go ahead and try completing the square. So what's s squared plus 6x, or 6s plus 32? I'll just write that as plus 6x plus, leave a space, plus 32 minus the same amount. And so that's going to be s plus half of that, 3. But 3 squared is 9, subtract a 9. This and this are equivalent. But 34 minus 9 is 25. That's nice, because the square root will be 5. So it looks like the shift here is going to be, since it's s minus -3, we're going to be multiplying everything by an e to the -3 and treating that as if it was an s. All right, so now let's put it all together. We've got 2s plus 5 over what's now s plus 3 squared plus 25. So I'm going to break this first by, this is the way I do it, pull out the 2, and then you can then say, make it s plus 3 minus 3 plus 5 halves, right? Which means we end up with 2 over times s plus 3 over s plus 3 squared plus 25, okay? And we've got this, which is a 2 times negative 3 plus 5 halves, which is going to be 2 times negative 6 halves plus 5 halves, which is negative 1 half times 2, which is negative 1. So you're going to have minus 1, and then just 1 over the s plus 3 squared plus 25. So if you treated this as an s instead, then that means that over here we have the form for a cosine. That cosine, yeah, that's right, just s on the top. So remember, we have to multiply everything by an extra e to the negative 3t to handle the s plus 3 shift. So we have 2 e to the negative 3t, and then this is a cosine of 5t. And then over here, now the sine version has to have the square root of this number here. So I'm going to have to fix up the constant here. There's a 5 on top and a 5 on the bottom here. So then I'll end up with negative 1/5 e to the negative 3t to handle the shift sine of 5t. All right. So right now we're just practicing handling this kind of a thing, because we're going to find that when we do complicated driving functions on the right-hand side of differential equations, we end up with situations like this. Okay, I have one last example for you for this video. Let's take a look. Let's say that we have a differential equation, so I'll show you how it looks when we're working a differential equation, okay? Second order differential equation with constant coefficients, which means we have various methods. We could use even methods from prior to spring break on this, right? But instead, we're going to do the Laplace transform method. So let's start with the Laplace transform of everything. So we know that the second derivative becomes s squared ys minus sy0 minus y prime 0. That's y double prime. And then we have to subtract 6 times the first derivative, which is 1s ys minus y0, right? And then we have plus 9 times y will become ys. And then I have this right-hand side. Okay. So this right-hand side is a t squared, right? But it's multiplied by an e to the 3t. So what we can do is treat this e to the 3t as a time shift, right? This is a is equal to 3. So everywhere where we see an s in the transform, we're going to switch from s to s minus 3. Okay, so that means we'll take the t squared only and do that, right? So t squared transforms into 2 factorial over s to the 2 plus 1, which is 2 over over s cubed, 2 over s cubed. But before we write this, we're going to take that t squared and shift it. So this is where the shifting comes in handy. We can just say 2 over s minus 3 squared. Okay. All right, so now we have the Laplace transformed version of the differential equation, which is an algebraic equation. We now want to solve this for ys, so we'll factor out all the y terms. So s squared minus 6s plus 9 times ys. And then let's go ahead and substitute in here. Y0 is 2, so these are 2. And this one is 17. Okay, so looks like we have minus 2s minus 17. And then negative 6 times negative 2 would be positive 12. So really this is s squared minus 6s plus 9ys minus 2s minus 15 equals 2 over s minus 3 squared. So first I'll move this to the other side. So we're going to get s squared minus 6x s plus 9 ys equals, we've got a 2s plus 15 plus a 2 over s minus 3 cubed, sorry. Yeah, cubed. Okay. And then we're going to now divide everything by this. So the ys is going to be 2s plus 15 over that s squared minus 6s plus 9, right? And then we've also got this 2, and it's got the s squared minus 6s plus 9 and the s minus 3 cubed on the bottom. All right. So what we can do here is, well, let's try to factor this. This might factor. What's s squared minus 6s plus 9? In fact, now that we've got to that, let me switch colors here. Too much one color on the screen there. What is s squared minus 6s plus 9? All right, well, that's the same as, I think that's s minus 3 times s minus 3, right? Yes, okay, so that means that we can write that as s minus 3 squared. So that means this can be written, and go back to this now, ys is s, or 2s plus 15 over s minus 3 squared, okay, plus 2, and since this is s minus 3 squared, and there's 3 more, this is s minus 3 to the 5th power, right? All right. All right, this one I think is going to be ready to go. We can take the integral by just, or the inverse Laplace by moving the 2 down and using this as a shifted version of 1 over s to the 5th. But this one might require some more work. We can try that split thing. We can try partial fraction expansion. Let's try the split thing. So what if I wanted to do this as s minus 3? I could say, again, I'm going to change colors here for this. 2s plus 15 over s minus 3 squared. If I wrote this as 2s plus 15 over 2, and then I split this into s minus 3 plus 3 plus 15 halves, s minus 3 squared, you would get, let's see, this is the same as 2 times 1 over s minus 3 squared. And then you would also get 3, well, 3 is 6 halves plus 15 halves times 2, which is going to be 21 halves. This is going to be 21. So plus 21 times 1 over, right, this is 2 times s minus 3. And this one's 1 over s minus 3 squared. Okay. Let me show you another thing here, too, that you could get. Let's see, is that right? 2, 11. Plus 5. 2, 1 over s. Did I do that right? This is 2 halves, 15 halves. So that would be 6, 21. Yeah, that seems right. Okay. You should also be able to do this with partial fraction expansion calculation. Let me, but I'm going to proceed. I'm going to proceed with this. You know, I have a different number on my key here, though. So let me just double check that. If I did the plus or minus 3, right? 2. This is s minus 3 plus 3. And then I did factor out this already, right? So that's 15 halves. Oh, it's not 15, it's 5. No, it is 15. Okay. Yeah, okay. Let me show you something you could do. If you don't like this plus and minus business, you should be able to also do this with a partial fraction calculator. So if you go to the mrfelling.com site and go to the applets and resources, should be able to use a partial fraction expansion calculator. And I realize now that I have a mistake in my key here. I wrote 5 when it should have been 15. Oh no, the mistake is actually in my answer right here. So let me back up. There's an error up here. This is 12, not 2, which makes this 5. Which makes this 5, which makes this 5, which makes this 5. And that means I need to redo this. apologize for this, but rather than redo the entire video, I'm just going to correct the mistake here. So if this was actually a 5 here, then we could take this, do that again, 2s plus 5 over s minus 3 squared. You can write that as 2 times s plus 5 halves, okay, which is going to be 2 times s minus 3 plus 3 plus 5 halves, which is going to be 2 times 1 over s minus 3. And then this one's going to be 3 plus 5 halves, not plus 15 halves. So that's going to be 6 plus 5 is 11 times 2 turns out to be 11. And then this is 1 over s minus 3 squared. Okay, if you don't want to do that, you're welcome to use a partial fractions calculator to do the same thing. Let me just show you what I mean. If I do a partial fractions expansion on just this, 2s plus 5 over s minus 3, we should be able to do a fraction structure here, 2s plus 5 over, and then parentheses, s minus 3, bottom here, this is where I need it to be, s minus 3 cubed. Okay, that should work and give me the same things. It's 2 times 1 over s minus 3 squared, and then 11 times 1 over s minus 3 cubed. Okay, it looks like I have another possible mistake in there I need to fix. This was cubed. This one is to the 5th. So this one would be cubed divided by 1. So that ends up being squared. And this one's cubed. All right. So that's the replacement for this. So now let me either through our plus and minus arrangement or through partial fraction expansion, we now have ys is equal to 2 times 1 over s minus 3 squared plus 11 times 1 over s minus 3 cubed. I had made some errors there in the, this was a cubed on the bottom, not squared. But I still have this term also, which is plus 2 times 1 over s minus 3 to the 5th. Okay, every one of these is in the form 1 over s, right? And, or 1 over s to a power. So let's do the markups for each of these, right? If you have 1 over t to the n, it's n factorial over s to the n plus 1, right? So whatever number is down here, right, this is going to be s to 1 higher. Since this is a square, this is going to be s cubed. Or going the other way around, if this is s is squared, this is going to be, well, I guess that one we can use the earlier table. Let's just do it one at a time. So 1 over s squared is t. So this first one is 2, but because we're shifted, we have to put the e to the 3t in there. And then 1 over s squared is 1 over s squared is going to be just a t. So that's going to be a t. So we should have a term which is 2 e to the 3t t. And I realized that my posted answer key has a mistake on it. So this is the correct thing. 1 over s squared would be t. So there's an extra t there. This one is going to be an s cubed on the bottom. So that means there's going to have to be a 2 factorial on the top and a 2 factorial on the bottom. So I'm going to have to multiply and divide. So I'm going to get an extra half here. This was 11, but now it's going to be 11 halves. 11 halves. And then this is the structure for t squared, but because there's a shift, e to the 3t. Same thing here, except this is with a 5 here, which is 4, so 4 factorial over 4 factorial. This is going to be 2 over 4 times 3 times 2. So the 2's will cancel and it'll be 1/12. And then this is the structure for t to the 4th. So this is what y of t is, the inverse transform of y. All right, so it looks like I might have some slight mistakes in the posted key on that one, but this one I now believe is fully correct. All right, that should be enough to let you try the problems. Apologize for the couple of bobbles there in the work on this one, but that just shows you how you can take something that would be hard to do. Uh, this would be very hard to do with the variation of parameters approach to deal with the right-hand side, but with Laplace transforms and the shifting, we can deal with that as a shift and just deal with the Laplace transform of t squared.